Hi everyone. Today we're continuing Module 3 and we're going to go over electrons again and where they exist around a nucleus. So we're going to start talking about electron configurations, which again just tell us where electrons are around a nucleus. So last time we saw a chart showing different energy levels for electrons. And we said that in energy level 1, there is an s orbital. So we're going to call this a 1s orbital. And then in energy level 2, there's also an s orbital. We're going to label this a 2s orbital. We also said that s orbitals are lower in energy than p orbitals, which are lower in energy than d orbitals, which are lower in energy than f orbitals. So also in energy level 2, there are 3 p orbitals, and they're going to be a little bit higher in energy than the 2s orbitals. So we'll call these the 2p orbitals. All right, then comes energy level 3. And in energy level 3, there's also an s orbital, so we'll call that 3s. There's also p orbitals, and those will be slightly higher in energy. We'll call that 3p. And then there's also 3d orbitals. And there are 5 of those. Let's see, 1, 2, 3, 4, 5. Oops. It's showing you future slides. All right, so we'll stop there for now, and we'll kind of fill this in as we go along. But these are the general energies of the different types of orbitals and sublevels. And we're going to start filling these in with electrons according to different atoms and how many electrons they have. All right, so what we just drew is called an orbital diagram. So orbital diagrams use boxes to show how electrons are arranged in the orbitals of an atom. So what we do when we're putting electrons in the orbitals is we fill the orbitals and energy levels from lowest to highest. So that's why it was important to show the relative energies of those different sublevels. So we're going to fill orbitals within the same sublevel one at a time, and then we're going to pair the electrons. So you'll notice down below we have the orbital diagram for carbon. And carbon has the atomic number 6. So that's the number of protons in the nucleus. But additionally, if we assume this atom is neutral, we also know that there are 6 electrons. So let's start filling in those orbitals. So we can see we've put 2 electrons into a 1s orbital, 2 electrons into a 2s orbital. And also notice that pairs of electrons have opposite spin. So remember, they have to have opposite spin. So we have an up arrow and a down arrow, which are representing a spin up electron and a spin down electron. Okay, so now we have 2 electrons left, and we're going to start filling in the 2p orbitals because those are next in energy. But instead of pairing up those 2 electrons in that first orbital box, we want to fill in each box with 1 electron first before we pair them up. So I kind of like to think about this as, electrons, they're all negatively charged. They don't want to be near each other. And it kind of reminds me of when I was younger And I did not want to share a room with my sister. I wanted to be in my own room and have my own space. So that's kind of similar to electrons. They want to have their own space if it's available. So, with the s orbital electrons, they don't have anywhere else to go. They're kind of stuck together. But in the 2p sublevel, there are 3 orbitals. There's 3 rooms. So we can spread out the electrons as much as possible. So we're going to put 1 electron in each room or box first before we pair up any other electrons. So now let's say we had 2 more electrons. So maybe we have an oxygen atom with 8 electrons. Then we would put 1 more electron in the last box, and then we would start pairing up electrons after that because there's nowhere else for electrons to go. So again, I like to think of it as sharing rooms with your siblings. Okay. Oh, can I not go to the next slide? Let's see if I can go back. Nope. Technical difficulties. There we go. All right, so this leads us to electron configurations. So electron configurations indicate the placement of electrons in an atom. So this is going to be different from an orbital diagram because instead of drawing pictures of where electrons are, we're just going to write out some numbers and letters. So these electron configurations also show how electrons fill energy levels and sublevels in order of increasing energy. So on the last slide, we saw that we had 2 electrons in a 1s orbital, 2 electrons in a 2s orbital, and 2 electrons in 2p orbitals. So we can actually write that as energy level 1, orbital s, and then we put a superscript 2 to show that there are 2 electrons there. And then we'll follow that with energy level 2, orbital s, and a superscript 2 to indicate that we have 2 electrons there. And then finally, we have energy level 2, orbitals p, and there are 2 electrons. All right, so that is our electron configuration. And that's also shown down below here. So we would read that as 1s2, 2s2, 2p2. Now notice that with the p orbitals, we're not indicating if the electrons are in a px, a py, or a pz orbital because they all have the same energy, so it doesn't really matter. All right. Now one last thing. There is an abbreviated form of electron configurations, and in the abbreviated form, we use a noble gas to represent a bunch of electrons, and that way, if you have a super long electron configuration, you can just replace most of the configuration with a noble gas. But we'll kind of get into that later, so don't worry about it right now. Okay, so let's start with the simplest atoms, hydrogen and helium, and we'll look at their orbital diagrams and their electron configurations. So hydrogen and helium are both in period 1 or row 1, and hydrogen has an atomic number of 1, so it has 1 proton and 1 electron. So hydrogen is super easy. We just put 1 arrow in its 1s orbital. And then its electron configuration would be 1s1. Helium has the atomic number 2, so it has 2 electrons, and we're going to place both of those electrons in the 1s orbital because it's the lowest energy orbital. So then we have the electron configuration 1s2. Now let's go to period 2 or row 2. So starting with lithium on the very left of this row, lithium has the atomic number 3, so that means it has 3 electrons. So then we're going to fill in the 1s orbital first with 2 electrons, and then we move on to the 2s orbital. So if we go back to our diagram that we drew earlier, I might give you a problem where I ask you to draw the orbital diagram for lithium. So then you would go to the periodic table and see that its atomic number is 3. So it has 3 electrons, if it's neutral at least. So then we know, okay, we have 3 arrows or 3 electrons, and we're going to start from the bottom of this energy diagram. Okay, so we're going to put 1 electron in the 1s orbital, and we know that the 1s orbital can hold a maximum of 2 electrons, so we'll put another electron in there, but it has to be spin down. It has to have opposite spin from the first electron. All right, so now we have 1 electron or 1 arrow left. So we're just going to go up to the next highest energy sublevel, which is the 2s sublevel. And we're going to put our last electron in that orbital box. Oh, I would not like to update my carrier settings. Okay, so we can then, from the orbital diagram, figure out the electron configuration for lithium. So we have 2 electrons in the 1s orbital, and we have 1 electron in the 2s orbital. So we have 1s2, 2s2, and that is our electron configuration. And that can be easier to write than having to, draw all of these boxes for the orbital diagram. Now, you might be wondering, if an electron is by itself, does it have to be spin up? Can it also be spin down? Yes. So there's a 50-50 probability that an electron will be spin up or spin down. So we could have just as easily drawn this single arrow as a spin down electron. That's totally fine. However, in chemistry, we typically draw the spin up arrow first and then the spin down arrow second. So yeah, most often we put spin up first. But it's just as likely that it could be spin down. So, oh, I'm going backwards. Okay, so back to our chart here. So as we move across row 2, we're just going to keep adding more and more electrons. So beryllium has 4 electrons. So we would add the 4th electron to the 2s orbital, and we'd pair up that single electron that we had in lithium. And our electron configuration would be 1s2, 2s2. Now, what if we want to abbreviate this? So let's look at the abbreviated electron configurations. So remember on the previous slide here, helium has the electron configuration 1s2, and that's always true. So what we can do is use helium as a substitute for those 2 first electrons. So you'll notice that for lithium, we had the electron configuration 1s2, 2s1. But we can replace 1s2 with helium, and we're going to put that in brackets to separate it from the numbers and letters. So then we end up with an abbreviated electron configuration of helium, and then followed by 2s1. Now, obviously, with these first few elements, abbreviating the configuration doesn't make a lot of sense because it doesn't look a lot shorter, right? But later on, we'll find we might have really long electron configurations, and it'll just be easier to put in a noble gas instead. Okay, so moving on to boron. Now we have 5 electrons, so we're starting to fill in the 2p sublevel. So we'll put the extra electron there in the 2p sublevel. And then carbon we already looked at, so we saw that there were 2 electrons in the 2p orbitals. And then we just keep going. So we've got nitrogen, we'll fill in that last box. Oxygen, we have 8 electrons, and there's nowhere else for that extra electron to go, so now we have to pair it up with one of the other electrons. And we usually go left to right when we're writing these out. So then fluorine has an extra electron that will go in that second box. And then neon, which is our noble gas, that has 10 electrons. So that very last electron will go and pair up with in the last box there. All right, so I am going to warn you to keep neon's electron configuration in mind. It is 1s2, 2s2, 2p6. Because now, when we go to row 3, we could use neon to abbreviate some of our electron configurations. Okay, so let's draw an orbital diagram. So nitrogen atoms are really important. We said before that they are one of the most abundant elements in the human body. And that's because they are found in amino acids, proteins, and nucleic acids. So let's draw the orbital diagram for nitrogen. So nitrogen's atomic number is 7, which means it has 7 electrons. And down below we have the orbitals for the first 3 sublevels here, so 1s, 2s, and 2p. So if you want to try this on your own first, feel free to pause the video and then we'll go over it together. Okay, so let's start filling in the 7 electrons for nitrogen. So we're going to put the first 2 electrons in the 1s orbital, and then we're going to put the next 2 electrons in the 2s orbital. So that takes care of 4 of the electrons, and then we have 3 electrons left. So we're going to put those in their own separate orbitals, because remember, electrons would like to be by themselves if they can. All right, so we've got 1, 2, 3, 4, 5, 6, 7 electrons. And then just as extra practice, let's write the electron configuration. So we have 1s2, 2s2, 2p3. Okay, so that's the electron configuration for nitrogen. All right. So now let's move on to row 3 of the periodic table. So sodium has 11 electrons. Its atomic number is 11. Now notice that in this chart, they just put neon in brackets before sodium's extra electron. So remember, neon has 10 electrons, and its electron configuration is 1s2, 2s2, 2p6. So we can use that as our abbreviation. So for instance, sodium has 1 electron in a 3s orbital, but its full electron configuration is 1s2, 2s2, 2p6, 3s1. Now, this is a bit of a longer electron configuration. So what we can do is substitute in neon for the first 10 electrons. So that's going to give us neon 3s1, and that's our abbreviated electron configuration. Okay, we can do the same thing for magnesium. Magnesium just has one more electron than sodium. And you can probably start to see the trend as we go down the list here. So we're just starting to fill in the 3s orbitals, and then eventually we start filling in the 3p orbitals, similar to what we saw before. Now, when we reach the end of the list, we get to our noble gas, argon, and that has 18 electrons. So it's completely filled in the 1s orbital, the 2s orbital, the 2p orbitals, the 3s orbital, and the 3p orbitals. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And we can abbreviate this by substituting the first 10 electrons with neon. So we get neon 3s2, 3p6. However, we can also use argon as or in abbreviated electron configurations for the next row of elements. So we always use noble gases to abbreviate. We never use any of the other elements, just the noble gases. Okay, so now what if we don't want to draw out the orbital diagram each time we're trying to figure out an electron configuration? So there's a different way to figure out the electron configurations for different atoms. And what we can do is kind of split up the periodic table into the S block, the P block, the D block, and the F block. So the S block, we have hydrogen and helium to start. We kind of moved helium over to the left. And remember, they have 1 electron and 2 electrons respectively, so they start to fill in the 1s orbitals. Then, when we get to row 2, we had lithium and beryllium. So their electrons start to fill in the 2s orbital. Then we move over to the P block. So we have boron. And remember, boron has 5 electrons. So its orbital diagram looked like this, and I'm just drawing half arrows for convenience. So boron already filled in the 1s and the 2s orbitals, and now it's starting to fill in the 2p orbitals, and it only has 1 electron in the 2p orbital. And then if we move on, we'll have another electron, so there'd be 2 electrons in the p orbital, and then 3, 4, 5, 6, until we get to the end for neon. So neon has 10 electrons. So neon has completely filled in the 1s and the 2s orbitals, and now it's completely filled in the 2p orbitals. So this is another way that you can figure out your electron configuration. So let's say, for instance, we want to figure out the electron configuration for aluminum. So aluminum is right here. So it is in the P block, and it's also in row 3. All right, so based on aluminum's location, we know that it completely fills in the 1s, the 2s, and the 3s orbitals. And it also completely fills in the 2p orbitals. And then there's just 1 extra electron in the 3p orbitals. Okay, so that means we have 1s2, 2s2, so we just went across here, and now we're kind of moving across here, 2p, and then we've got 1, 2, 3, 4, 5, 6. So 2p6. And now we're going to fill in 3s. 3s, 1, 2. And then we have one electron in the 3p orbital. So we've got 1s2, 2s2, 2p6, 3s2, 3p1. Okay, now what if we have, let's say, let's look at let's not even write down the element name. Let's just say we have this element here. Okay, so moving across, we know we're going to fill in the 1s orbital, and then the 2s orbital and the 2p orbitals, the 3s orbital, and we have 1, 2, 3, 4, 5 electrons in the 3p orbitals. So that would be 1s2, 2s2, and then 1, 2, 3, 4, 5, 6, 2p6, 3s2, and 1, 2, 3, 4, 5 for 3p orbitals. So this is another way to figure out electron configurations. And you don't even necessarily have to fill in those orbital diagrams to figure out the electron configurations. Now, another way to figure this out, let's say you kind of memorized, oh, 1s has 2 electrons, 2s has 2 electrons, 2p has 6 electrons. You can add together all of the subscripts here, and that will also give you the number of electrons. So for instance, we have 2 plus 2 plus 6, that's 10, plus 2 is 12, plus 5 is 17 electrons. So let's say I gave you an electron configuration and you had to figure out which element it was. That's another way to do it too. Okay. Let's see. So these are just some slides that kind of went over what we already went over. So they're there for you to read later, but we already went over that. Okay, so now period 4, we just keep going along. So potassium starts off row 4, and it has 19 electrons. So we're just going to start filling in the 4s orbital. And then calcium will do the same thing. But then what happens when we get to the D block? So let's go back. Oops. So what happens? Let's see. Oh, can I not erase? Apparently I can't erase. Well, what happens if we're right here in the D block? What do? We're actually just going to keep plugging along. So we're going to completely fill in rows 1, 2, and 3. And then we're going to fill in the 4s orbital and then add an electron to what's called the 3d orbitals. Okay, so this is where things get interesting. So I'm actually going to go back to our drawing of the orbitals. Oh, there we go. So normally we would assume that right after the 3p orbitals, we would have the 3d orbitals. That makes sense, right? However, what's really weird about this is that the 4s orbital is lower in energy than the 3d orbital. So the 4s orbital comes first. So we fill in 4s before 3d, which is really strange. However, if we look at the S block, P block, D block chart that we were going over, it kind of does make sense. So again, if we're filling in the energy level 3, we get to 4s before 3d. And the same thing happens if we jump down a row. 5s comes before 4d. So this is just something weird about the periodic table and electron energy levels. This is just something that experimentally scientists figured out. They figured out that the 4s orbitals are actually lower in energy than the 3d orbitals. So you'll also notice that even though this d orbital is in row 4, it's labeled as 3. So the d block starts at n minus 1. So it's a little bit strange that way. Okay. So then here's the 3d block. And we're going to kind of skip over this for now. And we're going to go on to our learning check. So let's use the periodic table to determine the symbol and name for the element with the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Okay. So if you want to try to figure this out on your own, you can. And then when you come back, we'll go over it together. Okay, so let's figure out which element we have here. All right, so I'm going to go back to this chart here. Let's see if I can erase now. Yay, okay. Technology is supposed to make things easier, but it's not always the case. All right, so we found, or we had the electron configuration that ends in 3d7. So that's what I'm going to focus on. It ends in 3d7. So we had, some other information here. Okay, so that means that we're in the 3d block. So we're in the first row of the transition elements. And what's really great here is I can just count over. So I can go 1, 2, 3, 4, 5, 6, 7. So whatever element is right there, that is my element. All right, so oh, here we go. So there are 7 electrons in the 3d sublevel. So again, we're just going to count over 1, 2, 3, 4, 5, 6, 7 on the periodic table in the D block, and that gives us cobalt. Now, the other way you could have figured this out, you can just add all of the superscripts together. So we've got 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 7. Okay, so that gives us 10. Whoa, I don't know how that keeps happening. So we've got 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, 20, 27. So there are 27 electrons in this atom. And if it's a neutral atom, that means we also have 27 protons. And on the periodic table, cobalt has the atomic number 27. So that works out. So that's another way to figure it out too. Okay, so I think we're going to stop there today. Let's see. Oh, actually, let's do one more problem. So I encourage you to try to write the electron configurations for the following elements. So carbon, silicon, and oxygen. And the solution slide is on the next slide, so you can check your answers. But I think I'm going to end the video here. There's also a activity sheet on Canvas. So it's called the Electron Configuration Worksheet. And normally if we were in person, I'd have you all fill it out together and kind of work on it as a group. But what I'll do instead is post a video going over that worksheet so you can kind of follow along, or you can check your answers and make sure that you have the same thing I do. Okay, so again, if this is super confusing, don't worry. This is a tough subject. This is probably one of the tougher subjects this quarter. So feel free to contact me and set up an office hour if you want to talk about this more, or contact the Writing and Tutoring Center. They are awesome. They can also help you out. But otherwise, I will see you in the next video.